Hello, welcome to the StatEase webinar. This webinar title is Multiple Response Optimization Unveiled. My name is Sherry Kraber, and I am a statistician here at StatEase. And I wanted to be able to share with you some of the under-the-cover things that you might want to know about optimization. I will not be covering any statistical analysis in here. I will be bringing in a file that has the data already analyzed, so I can spend the time focusing on the optimization routine itself. If you want to learn more about the analysis, we have other webinars that are pre-recorded that you can go to and learn some more about that. But I'm happy to have you all here with me today. As you see, I have kept you all muted. We have a lot of people on the line with us, and so we're going to keep you muted, but the question box is available and you can type questions in there. I will try to keep an eye on it. If I don't have time to get to your question, I will definitely reply after the session via email. Questions may also be sent to stathelp@statease.com. If you send a question, please provide your company name, and if you're using Design Expert, we'd appreciate having the serial number, which is found under the Help About screen. These slides and a recording of this webinar will be posted on the webinars page of the StatEase website within a couple of days. You will get an email that tells you the link to that recording. The data file that I'm using for this talk can be found in our help system. If you go into Design Expert, go to Help, go to Tutorials Data, and look for the data file that's called Conversion. So you can duplicate everything that I'm doing here in this webinar. So we are going to do a brief check of the RSM analysis to make sure it fits the minimum criteria needed to do an optimization. And then we will go through the basics of optimization, including the desirability function, how that works. That's often a kind of a black box mystery to people. And the concept of searching the design space, which is something that we don't teach in our classes very much, but I've dug out some great graphics on how the design space search is done, and that answers the question of why you get so many solutions. If we have time, we will wrap this up with a brief glance at graphical optimization. So let's go ahead and get started. The case study that we're using is a chemical process that has two responses. Numerical optimization is generally used when you have multiple responses that you have to simultaneously optimize. So we have two responses, the percent conversion and the amount of activity. There are three factors involved in the study: time, temperature, and a percent catalyst. And this is run as a central composite design. Optimization can be done with any design that you use, whether it's a factorial design or a response surface or a mixture design. When you go through and do your analysis, the basic procedure is to generally start with no transformation. We usually don't know that we need one right off the bat. Then if you are doing a response surface design like this one, you would look at the fit summary. The fit summary is a great place to look at comparative statistics. So you can compare the linear model, the quadratic model, potentially a cubic model if you're able to fit it. But in general, we say start with the suggested model. The software has a little algorithm built into it to provide a suggestion based on these statistics. Then you proceed to the model button, and you select the model that you would use, generally the suggested model, that will be the default. And then in the ANOVA, you can check to make sure that the p-values are good and that you have good summary statistics. We're going to look at that here in this class just briefly. And then you'll follow that up with checking out your diagnostic graphs. I'm not going to cover diagnostics at all in this webinar, but that's not to say they're not important. The model graphs then will graphically show you how the response is being fit by that polynomial model. And so you repeat this process for each of the responses that you have. The first step, of course, is to make sure that you have decent models. They don't have to be perfect. They don't have to be, everything, just as a textbook, because you're dealing with real life, and real life doesn't follow a perfect polynomial. So we say don't overinterpret the statistics, but basically you would want a significant model, which means the F value should be large, and that would give you a p-value less than 0.05 as a general rule. Some people might want p-values even smaller than this, 0.01, but that's for you to decide what you want your p-value to be. You also want insignificant lack of fit. Now remember, you're only get a lack of fit test if you have replicates. So if you've modified the design and you don't have replicates, then you won't get this lack of fit test. But it's a good thing to have, and I really recommend making sure you do have a few replicates in your design. Generally, we say 5 or so is a starting point. And that should be a small f value with the p-value greater than 0.1. And then reasonable agreement between your adjusted and predicted R-squares. By reasonable agreement, we want them to be within 0.2 of each other, just as a general guideline. And certainly higher is better. What value do you want to do numerical optimization? My rough rule of thumb is about 0.5 or higher, especially with a predicted R-squared, would give me reasonable confidence that I am able to make predictions that will be meaningful in the future. So again, that's kind of up to you to decide, but you don't have to have R-squareds that are 0.9s. You don't have to go that far. And then adequate precision is a signal to noise ratio that we generally want to be above 4. And as I mentioned, we want your diagnostic plots to be well behaved. So the analysis of this data set, like I said, you can get this data set out of the help system. But the quadratic model for the conversion response ends up with 9 terms in the model, has a p-value of 0.0001. So that's very significant. That's great. And the lack of fit is 0.85, meaning it's not significant. So we have a check there, check there. The adjusted and predicted R-squareds are both high and within 0.2 of each other. Again, the adequate precision is greater than 4. So this checks all the boxes that we need to be able to use this in the numeric optimization. The second response is activity. And again, the model is significant, less than 0.0001, so very, very significant. The lack of fit is not significant. It's also good. And look at these R-squareds. These are 0.9s. They're great. This is a linear model, and it fits activity very, very well. So it's a great candidate to go into numeric optimization. So with that introduction to the problem, let's jump into the optimization, which is the key here. So optimization can be found underneath the analysis portion. We will click numerical. We have some goals here. We want to maximize that first response conversion to be greater than 80%. And we want to target the activity level to be a 63 with a range of plus or minus 3. So those are the goals that we need to enter into Design Expert. And I am actually going to open this file and go to optimization. Let me just do a quick show of hands here, at least a few of you. If you can confirm that you are seeing my Design Expert screen, I would appreciate that. Great, thank you. In optimization, you can see in this criteria that we have all the factors listed. Now, although the factors could have goals set, I don't recommend that we do anything with those to begin with. You first start by putting goals onto your responses. So the first response was conversion, and the choice of goals are the default of none, and then we have maximize, minimize, etc. We're going to use this maximize. The other default is in there is that the limits are set to the ranges of the response. So the lower limit was originally set to 51 and the upper limit was originally set to 97. Now, these limits come in as the default, but they are rarely what you want to leave. They work, but I highly recommend that you change them to be more reflective of what you actually want out of the process. So since I want to maximize conversion, I want my lower limit to be the minimum conversion that is acceptable. So when I look at my range, well, although I measured some conversions of like 51 and 60, 70, that's not acceptable to me. I don't want to get solutions that have that low of conversion. So I want to set that lower limit to be a boundary. And so I'm going to say it's 80. So 80% conversion is the minimum acceptable solution. So that's really a stopping point, as you'll see in just a little bit when we get to the desirability functions. The upper limit, the default was 97, but I'm actually going to give this a stretch target to be 100%. If I could get to 100%, that would be awesome. Okay, I will get back to answering the question of what are the weights and what are the importances here in just a little bit. But first of all, my second response. This is activity. We want activity to be a target of 63, and I want a range there of 60 to 66. So again, I don't want to leave these defaults of 53.2 and 67.9. That's not the acceptable range. When you use optimization, you really want to think about what is acceptable to the process or what is acceptable to the customer and really define this. That's controlling the optimization so it does what you want it to do. Okay, so after we define those, then we click on the solutions. And there are two ways of looking at, well, there's three, but two ways that are really effective at looking at these solutions. The default view is the ramps view. And the ramp looks at each solution one at a time and gives you the kind of a picture view. So I can see that for this first solution, my time is set just to the right of the midpoint of time at 47 minutes. Temperature is set at the far right side at 90 degrees, and catalyst is at 2.68, kind of about 2/3 of the way over. With those process settings, I then get a percent conversion of 91% and an activity right spot on at 63. So this is a good picture view. It's nice to take this out into a document. And by the way, you can do that by right-clicking, and you can either copy or you can export these graphs to Word or PowerPoint. Either way. The alternative view is the report view. So the ramp just shows you one solution at a time. And over on the factors tool, you can click through all the solutions and look at them one at a time. The report view gives you a summary of all 15 of those solutions from top to bottom. So again, time 47, temperature 90, catalyst 2.68. And they are ranked by something called desirability, which we'll get into next. And we will just looking through these, I can see that there's a break in here, right here, where I've got first all the temperatures 90, and then all the temperatures at 80. So you can see there's kind of two halves to this, two solutions that are different from each other. All right, so let me toggle back to the slideshow. And just a note on this slide, solutions are reported by desirability. They're ranked by desirability, most to least, which is based on how well the goals are met. The closer all the goals are met, the higher the overall desirability will be. So let's dig into desirability a little bit more. The desirability is a mathematical function that allows us to search for good combinations of responses. And it is a geometric mean rather than an algorithmic mean. So a geometric mean looks like this, where we have the big desirability for the overall solution equals individual desirabilities for each response. So I will have a desirability for conversion and a desirability for activity and all my other responses. These mini desirabilities are multiplied and then taken to the power of 1 over the number of small desirabilities. Okay, so this is called a geometric mean. These little d's range from 0 to 1, just like the big D does, which is least desirable to most desirable, and is the number of responses. Now, one really key point here that people forget is that desirability itself is not a statistic. We're not actually trying to optimize desirability. Desirability is just a numerical tool that helps us evaluate how closely the responses meet the criteria that you assign. So, it's actually fairly simple to change desirability by changing the criteria. So we don't want to get focused on getting a desirability itself of 1 or close to 1. The solution with the highest desirability in the set is the best solution, whether that desirability is 0.5 or a 0.8. It's just a tool for ranking the solutions. Okay, so we'll get into more details shortly, but we can search for the greatest overall desirability for both responses and factors. If we get an overall desirability of 1, that would indicate that all goals for every single response and factors, if you are optimizing those two, are perfectly satisfied. And honestly, if that happens, you're probably not asking for enough. A desirability of 1 doesn't impress me. It tells me that, hey, it's possible I could get an even better solution if I just push my criteria a little bit farther. A desirability of 0 will occur when 1 or more of the responses falls outside the acceptable limits, meaning you can't get to even the minimum criteria that you set. And hopefully this doesn't happen, but if it does, then just relax some of your criteria and open up the space a little bit. Okay, so correctly or setting the criteria well is the critical part of numerical optimization. We want to define the goal. We want to define the limits. And so I've already said the criteria for this example, but let's look at how these define desirability. So for instance, the maximize goal. If we choose a goal maximize, desirability works like this. Desirability is going to be 0 if the response at a particular point in the design space, if the response is less than that low limit. So anything below this low limit is a 0 desirability. If the response ends up being above the high limit, then the desirability is 1, equally anywhere beyond the high limit. Even though you set the goal of maximize, when you define the high limit, you're just saying everything is equally good at that, above that high limit. Then desirability ramps from 0 to 1 in a linear manner by default as we go from the low to the high limit. Okay, the target goal gives desirability of 0 if you are either below the low limit or above the high limit. We get a desirability of 1, the perfect desirability, only at the exact target. And then we ramp desirability from 0 to 1 as we're either going from the low level to the target or from the target down to the high or up to the high limit. That's another ramp from 0 to 1. So a goal really forms this little tent of desirability. Okay, so those are the 2 we used. Minimize is another goal that works just the opposite of maximize, where really the high value is the limitation. We don't want to go above the high value when we're minimizing. So anything above the high value is a desirability of 0. And then there is a ramp from 0 to 1. All right, the goal of in range provides you with just a really simple, everything is good. So all desirability is 1 in between the range that you set. So everything is equally good, and we're at desirabilities of 0, below the low limit and above the high limit. If you set a goal is equal to, and this is only available for a factor, but it's really convenient sometimes to do for factors. You can set a goal is equal to an exact value, or where I really like to use this is with categoric factors. Maybe in my DOE, I was comparing vendor A, vendor B, and vendor C. And in the optimization, I decided that vendor B was best. And so I would set the goal for that factor to be equal to vendor B, and then I can optimize just around that one vendor. So then desirability is at 1 for that particular setting. The default goal for any of the responses is simply none, and that will cause the response to be ignored during the optimization. And so this is great when you have some responses that have poor analyses, that don't meet that kind of minimum criteria. I suggest that you set real goals only on the most critical few responses first and make sure you get some solutions. And then you can add the responses that maybe did not have as good of analyses or are less important to your process. All right, now, weights and importances. Let me jump back to the software because it's kind of fun. Weights go from 0.1 to 10. And so for instance, on target here, the weight is the way that we do the linear ramp. And right now, the weight is set to 1. So if I take this box, I can actually drag it down and it increases the weight. You see that? Now it's a weight of 10. And by doing this, this makes the desirability stay at 0 for a much longer time. And it's not actually 0 beyond 60. It's a tiny, tiny little bit above 0, but it stays very, very low until we get close to that target. And so effectively, this is going to push solutions to be close to that target. So we could pull both of these sides down and make a very, very tight desired target. So weighting gives more emphasis to the goal if you increase the weight. Now, we can also lighten up on the weights and push them up to or down to a 0.1. So we lessen the weights, and you can see how that brings desirability up. So it's very good, kind of in a broader range. This actually makes it more like an is in range goal, with still trying to get to that target of 63, but we don't mind if it goes off of 63 a little bit in either direction. Okay. And one final way of using this, I might use this if I have kind of a one-sided specification. Maybe, although our target is 63, we say it's okay to be a little bit above 63, but we cannot be below 63. Then you might want to do something like this with your weighting, where you're allowing the function to err on the side of being above 63 is okay, but below 63 is not, because it's going to reduce the desirability very, very quickly. So these one-sided specs, that's my favorite place to use weighting. Okay. To be very, very honest, I rarely change the weights to be anything other than linear. Weights are just, they're a nice little tweak, and there are definitely times to use them, but I don't use them very often. Okay, so there's a few slides on here. How about importance? Importance is my favorite. Definitely use importance. Importance is the relative importance of one response versus another response. So it's putting a relationship between the responses. Weighting only affects that one single response and how the optimization is getting to the desirability on that one thing. Importance pulls all the responses together. So if you have 10, 15 responses, I suspect that you have 2 or 3 that are critical responses. They should get importance of 5 stars. Then you probably have some moderately important responses. They can stay at the default of 3 stars. And maybe you have some very low importance responses that could get a 1-star rating. These stars operate as exponents in the desirability function. So you can see the little R1, R2 to Rn. So these would be 1 to 5 stars and helps drive the desirability to favor the most important responses over the least important responses. So again, back on our responses, we could set this importance for conversion to be 5-star. That would give it more importance over activity. Okay. For these results, I am going to leave everything at the default of 3 stars. And if everything is at the same setting, then it doesn't matter. It doesn't matter if they're all at 1s or they're all at 3s or all at 5s. If they're all the same, then the function reduces just to the basic function and they're all treated equally. Okay, so let's recap the desirability first, and then I'm going to get into the search function. So if you get a desirability of 1, that either means that your wildest dreams have come true, or more realistically, you should set more demanding criteria. You can ask for a little bit more out of your system because you haven't actually found the real optimum yet. A desirability between 1 and 0 means all of the responses were within acceptable limits, but at least one was not perfectly achieved. And then if you get a desirability of 0, that would indicate that 1 or more responses falls outside the limits, and you're unlikely to see desirability of 0, but what you may see is a message that says no solutions found. I've gotten that, no solutions found. That means that there was no place in the design space that met all the criteria that you set. So you need to go back and relax some of the criteria. All right, so let's talk about searching the design space. And I've kind of put together some graphics to illustrate this. Some top level things. Numerical optimization is basically a hill climbing technique. And all the major software packages for DOE use the same or very, very similar techniques that I'm going to show you here. It's a very, very powerful technique and works well, which is why we've all used it. We can have more than one hill. We can have in the design space, there can be plateaus and mountains as you have many responses that all have different response surfaces. We are trying to combine all those response surfaces into one multi-dimensional design space. So it's a very complicated space to search. So to increase the chances of finding all the possible optimums, we do several optimization cycles. In this particular case, we have 9 unique design points in the design space. We use those, and then we add 100 additional randomly selected coordinates to be starting points. Now, if you were to take this same data file, you would actually have the same 9 unique starting points, but your 100 randomly selected coordinates are randomly selected. So your starting points, every time you run this, are going to be slightly different from that perspective. The design points remain the same, but the random extra ones are going to be different. All right, so our design space can be very complex. And so I just kind of made this for fun. This mountainous region. So we have this mountain and we also have a plateau down here. And we're going to send an airplane flying over this, and we're going to have parachutists, skydivers jumping out of here into the mountains. And these are all planting seeds in your design space. So remember, this is a very multi-dimensional design space. We have to plant seeds. So those are the 109 points that we planted. Then when the skydivers land, they have to look around their area and they have to walk up. They are told to walk up. They are told to walk towards increasing desirability. So they look around their area and they test. They take a little step one way and another way and all different ways around them, and they're kind of testing and looking to see where desirability is better than where we're at currently. And they walk up from there. So if you're on a mountaintop, it's fairly easy to figure out that you're going to walk up towards this peak. But I can see that these two guys are probably both going to end up at this same peak. And these two red X's, they're going to end up probably on that peak, although notice that there's another peak very close by that this guy might stop on. So as a result, we could get a couple of very, very similar solutions that are not identical because we get very close. Now, it's even worse if you have a plateau. When you have a plateau and you're looking to increase desirability, but desirability is kind of pretty much all the same all around the plateau, it's hard to know which direction to go to. So you, with a plateau, will have even more solutions that are just spread across the design space. And you know what? Quite frankly, that's good news. That means that you have a very robust design space, and there are many places where you can make product that meets your criteria. So I know that people are often looking for optimization to give them the one answer, but having a lot of solutions that meet your criteria is a very good thing. It means you have a very robust design space. One unique solution means that you've got to get those process settings exactly at those settings in order to have acceptable responses. Okay, so now this is some of the details that we don't normally talk about in class, but it's the behind the black box details. I'm going to roughly go through them, and then when you get the slides, you can read through this and kind of think about it on your own. It's a bit of a mind bender, but this is using a simplex hill climbing algorithm, which starts with where that red X started. That's the centroid. And then, as I said, it takes a little test and forms a simplex around that space and checks desirability. So we're just going to say that this location was the best desirability we found. This is the worst desirability we found, and this was the next to worst desirability that we found. We're going to take a big step away from the worst vertex. So from this worst, we would actually take a step that would be over here to the right of the centroid. Then the next step we would take would reflect away from the next worst thing. So we're going to take these jig-jagged steps around the design space. So in 2D, our first move would be to this opposite corner. And in 3D, our next move would be opposite over here to this other new point. And then we have to take other moves. So kind of for fun, whoops, sorry, 2 pages. This is the simplex moves that would happen on a response surface contour plot. And so we are moving over here and then over here, and we keep moving until we eventually start circling in on the center and we stop. So we find that peak. Okay. Now think this is done from one starting point, and we have 109 starting points in this design space. So, it's happening many, many, many times. All right. Now, to be honest, this isn't quite what we do. This is a simplex move. We actually do a variable sized simplex, which was developed by Nelder and Mead back in the 1960s. So this allows us to both expand and contract depending on the desirability. So basically, if we test a spot and desirability is even better than what we expect, then we take a bigger step and we go farther out. So like here, this is an expansion. This step was good, so we want to go even farther out. On the other hand, if this step was not so good, then we're going to hesitate and we're going to come back a little bit. That's called contraction. So we just actually come back in because we don't want to overstep where we're going. We want to make sure that we're honing in on the best solution. So this variable sized simplex allows us to both expand and contract based on our testing of the desirability and wanting always to go up and not to get worse. How fun is that? Okay, here's what the slide looks like then. If you apply that enhanced variable sized simplex method onto that same contour plot, and you can see that we expand and we expand and we contract a little bit, and we really hone in on the exact optimum. So, this underneath the covers is a very, very sophisticated algorithm going on, lots of fun, and very effective in exploring the design space. I frequently get asked, well, should I, expand the number of random starting points, because we're at 100 by default. And the answer is, well, you can. I actually don't find a need to do that very often. And that's because of this complex algorithm that's being used, because we are really exploring the design space very, very well with these 100 points. But certainly you can, if you think you have an even more complex region, you can do more. If you want, it just takes the computer a little more time. So again, numerical optimization is basically a hill climbing technique, and we can have more than one hill. And due to the variable step size, the final stopping point of each cycle will differ by small amounts. And this results in multiple solutions that are very similar to each other. And, this should not give you grief. It should be good that you're just really finding this spot that's very good. And probably your process cannot be as sensitive as the number of significant digits that are shown in the computer. So just find a good solution and round it, and that will work for you. So back to our case, our solutions, we found two distinct solutions at 90 degrees and at 80 degrees. And you can see that the time varies just a tiny little bit by 0.3 minutes. And catalyst varies by like 0.06. With the 80 degrees, you can actually get by with a slightly lower time, but a slightly higher catalyst. So small differences there. Conversion is a little bit higher at the 90 degrees than it is at the 80 degrees. Activity is met perfectly at 63 in both instances. So the desirability ends up being a little bit higher, 0.752 versus 0.608 on these two solutions. And here's how desirability is calculated. So for conversion, the small d for desirability, we get to 91.3. So we take the 91.3 minus the 80, divided by the range of 20 is 0.565. Basically, it's saying you're 56.5% of the way up the slope. Then for activity, we hit 63, so we got the perfect little d of 1. Then we take those two and multiply them together, raise them to the 1/2 power to get our overall desirability of 0.752. Okay, so that's how the overall desirability is calculated for this particular case. Picture-wise, this is a graph of desirability. Now, I don't usually graph desirability because it's not the response that I'm interested in, but just to show you the two peaks that we're doing here, one at the 80 degrees and the one at the 90 degrees. You know, it's a good display in this case. But the real graphs that you'd want in your reports are the graphs of the responses themselves. Okay, some tips for using numerical optimization are make sure that you change the default upper and lower limits to represent your expectations, especially cutting off those unacceptable response values. That's really, really key that people miss. Use importance to prioritize your responses. And if you have a lot of solutions, well, tighten up the criteria. Or maybe you add criteria for a few select factors. Don't add too much, but just maybe a few. And finally, remember that desirability is not a statistical function that must be high. It's simply a mathematical tool to rank your solutions according to how closely they met the goals that you set. Okay, before I go to the graphical optimization, which I'm just going to look through briefly, I will answer one question that I see came in, which is how to change the number of starting points. There's this options button right on the front screen, which allows you to change the random starting points from 100 to more. And this is the maximum number of design points that are used. The specific points you cannot edit. All you can edit is the number of points that are used. So you can use design points, and then you can change the number of random starting points. There's a few other things. The only other thing that you could consider changing might be this duplicate solutions filter, which is the amount of difference, the difference between response values that are considered to be the same solution. So increasing this will make a larger difference and reduce the number of nearly identical solutions. And then decreasing this number will increase the number of nearly identical solutions. So 0.5 is the default. If you get tired of seeing so many nearly identical solutions, you might increase that number, maybe to 0.7 or something. You could try that. But I find these defaults really, really, really good to use. Now, these options have been around since version 9, 10, 11, 12. So even older versions of the software will have these. Optimization hasn't changed that much, but there are a lot of other really new features, nice new features in design in version 12 that are good to have. We will be releasing version 13 with even more new things, either fourth quarter or first quarter 2021. We will be stopping the support of version 9. If you're still on version 9, we will be ending the support for that at the end of this year. So if you're still on that version, you'll definitely want to start looking into upgrading this fall. Now, let me move on to the graphical optimization. If you have already done numerical optimization, then your goals will carry forward into the graphical optimization. So here, my lower limit for conversion is 80. And that's the only stopping limit, so that's the only limit that is important. For activity, we use the 60 to 66 because that's the range that's acceptable. So we're really just looking at acceptability here because we're just going to get an overall picture. And I am going to switch this to the AC view because it's a little more interesting. So here's the picture of the time versus catalyst for either 80 degrees or I'll put it on 90 degrees. Because this was 90 degrees was the better temperature. Okay, now if you think about it, this design space is good, but operating near these boundaries is probably going to end up giving you some unacceptable solutions just due to the random process variation in your system. So one of my favorite features that didn't exist back when I was working on DOE as an engineer at 3M is the ability to add confidence intervals onto this. So I'm going to show you how to do that. Back on the criteria screen for conversion, all we have to do is click on this extra button here that says use interval, and it will add a 95% confidence interval onto this. You could also do prediction intervals or tolerance intervals. I won't get into those, but they are options. And I also want to add the interval onto the activity. So I'm going to add those two confidence intervals in, and that results in graying out just a little bit of that design space. And now I know that when I operate within the yellow here, I'm going to get consistently good product. Not just my mean, but my individuals should also be in really good shape too. So it's just a way of kind of controlling and making sure that you're in a really good spot. So that covers the rest of these slides. To wrap this up, numerical optimization helps us find where the response requirements are simultaneously satisfied. It's very mathematically intense under the covers, but it's easy to use from a user standpoint. Graphical optimization is very, very old school, and it's simply superimposing the response contours on top of each other to graphically see which response criteria constrains the optimum. These give you really awesome graphs to put in reports and to show other people so they can really picture the design space and use them perhaps to run your processes. You can add the confidence intervals to build robustness into this design space and really keeping you away from the edges. So this wraps up the educational portion of this webinar. I would like to point out that we offer a variety of resources for you, including other pre-recorded webinars on our website. We offer distance learning training. Now we've converted everything to distance learning, and offer the modern DOE for process optimization. That's the perfect class if you are doing process work. Or if you are working with formulations, then I would recommend our mixture design class. If you have a team of people, 6 or more people, you might want to consider a private session. This allows you to choose your date and time that you want to hold the class. And you can even add some company case studies into the class, and we can discuss those together. For any way, this is a great way of improving your DOE skills. And the topics are applicable both to novice and advanced practitioners. So I would encourage you to explore our website. If you sent in questions that I did not have time to answer, I will send you an email after we are done and take care of those via email. But I want to thank you for staying with me today and look forward to seeing you again. We do have a new user webinar, an intro to Design Expert software, this Thursday. So I would certainly welcome you to attend that. You can find that on our website under the webinars category. And we will be having a series of educational webinars all through the fall. We're really trying to do these every month now. So please look for them. If you haven't signed up for our email list, you can do that on our website too, and then you'll get a notification each month as the webinars come up. So with that, I'd like to thank you for attending and wish you the best on this really great day. So, thank you.